Hello. In this video, we're going to talk about some applications of the derivative. Okay, so you might remember we already touched on one application, which was related rates. Okay, how rates are related through derivatives and implicit differentiation. But now we're going to use derivatives to analyze functions, full-on functions, and analyze properties about them. Okay? So, what we're going to learn about is extrema. Okay? This will be kind of a long one since extrema, this long video, because the topic of extrema is really important in calculus. Okay? So, what I'm going to do is draw a little function f. Okay? Excuse me. So, we're going to draw a little function f. Okay? So this will be our function f. Okay, this will be our function f. Okay? So an extrema is a point. Okay? It's a point where the function reaches a maximum or minimum value. Okay, so our first topic when studying extrema is on an interval. Okay? On an interval. So what we're going to do is we're going to pick a random interval. Let's say from A to B. Okay? A to B. So that means this will be f of A. And I shouldn't have picked points that are this close, but f of B is a little smaller. Okay? So if we want to find extrema on an interval, first, how do you even find extrema? Okay? Or how do you find these extreme points? First, you have to find critical points. Critical points. Okay? What a critical point is where f prime of x, yes, is where the calculus starts to come in. F prime of x is either 0 or undefined. Okay? F of x is 0 or undefined. Okay, so like if you had a function like this, this is your b, this is your, I'm just say 0. This would be a critical point. This would also be a critical point. So if you have a and b, this will be a critical point. Any place where f prime of x is equal to 0 is a critical point of f. Okay? And you can kind of see why you have to set f prime of x equal to 0. If you kind of remember algebra, and you remember how a parabola works, you might remember what the vertex is. The vertex is this minimum point. Look how the graph starts to decrease, but then starts increasing. But there's this one instance where it's completely horizontal, where f prime of x is equal to 0. F prime of x is equal to 0. And when f prime of x is equal to 0, you can see that it's at a minimum or a maximum point. This can also work for a downward facing parabola. Okay? So when f prime of x is equal to 0, there is a pretty good chance that it is a maximum. The reason why I say chance is once you find all the critical points of the graph, all the critical points on the interval, then you have to test all of them. Okay? So you have to test f of A, f of B, and if the critical point occurs at x equals c, at x equals c, let's put c over here. This I put 0, but that's also c. Okay, at x equals c, that means you also have to test f of c. F of c. Whichever one of these points is the largest out of all of them, if f of A is the largest, on that interval, it is the absolute maximum. That means it is the highest and the largest the function will ever evaluate to on that interval, not the whole function, okay, but on that interval A to B, okay, on this interval, we're focusing on this interval. It's the largest the function's ever going to get. If f of b is the minimum, that means it would be the smallest one of them. It would be an absolute minimum. If any of one of the points were absolute or the smallest out of all three of them, you have an absolute minimum. And f of c is their critical point. Okay. So you have an absolute maximum, absolute minimum. Keep in mind that there can be more than one critical point. Okay. You can have an interval of this size from here to here. That means a 1, 2, shouldn't have used yellow, and this. These 3 will be critical points, and you check 5 values. Okay, so you have to check the end points of the interval as well as the function evaluated at each of the critical points. Okay, so if we were to take our example over here shown by the red box, you can see that B is the smallest, okay, just a tiny bit smaller than f of A, but still the smallest. So f of B will be our absolute minimum. A relative minimum we'll cover a little bit later. Absolute minimum, okay? So which one is the largest on this interval? Well, if we look at f of A, f of B, and our critical point over here, you can see that the critical point, just looking at the graph, is our largest. So on that interval, it is the absolute maximum. And f of A is unfortunately nothing. Okay, it's just right in the middle. So f of B is our absolute minimum. F of C is our absolute maximum. So I accidentally said relative minimum and relative maximum, and that is what we'll be covering up next. Okay, so we're going to cover relative extrema. Relative extrema. Okay? And this is on an unbounded interval. The full function we're going to be looking at. Okay? So when finding absolute minimums and minima or maxima, you have to look at a closed interval, an actual range of numbers. But for something like this, you have to look at the whole function. Okay, so here's our second arbitrary function. Okay? So a relative maximum and a relative minimum is kind of the same, okay? And to find those, first you have to find your critical points. Critical points. Take the derivative of f of x, f. Take the derivative of f of x, we have f prime of x, and set it to 0, or find what values of f make the function undefined. So what values of x make f prime undefined? Not the function, but what values of x make the derivative undefined? Okay? And number 2, this is relatively new to relative extrema. You have to test if it's either a maximum or a minimum or not at all. Okay? So we're going to try it on this function over here by basically eyeballing the points. So you're here, okay? And we have a point here, critical point here, what seems to be a critical point over here, one over here, and one over here. Okay? Now you have to use what is known as the first derivative test. This one is a big one, okay? Because it tells you what type of point it is. Is it a maximum? Is it a minimum? What is it? Okay? So what the first derivative test basically says is that if you have a critical point at x equals c, some number c, then if f prime of x goes from negative to positive at x equals c, so it goes from negative to positive at x equals c, that means it has to be a minimum, a relative minimum, not an absolute. You can't find an absolute maximum or minimum because the function can go infinitely, like it goes to negative infinity or positive infinity. So there's no absolute minimum or maximum. It's relative. It's a relative minimum at x equals c. If f prime of x goes from positive to negative, at x equals c, then you have a relative maximum. A relative maximum at x equals c. And if f prime of x just does not change signs, if it does not change signs, nothing. It's not a maximum nor a minimum. Neither a maximum nor a minimum. That point is a dud. Okay? Doesn't tell you anything. It's just a point where the derivative happens to be 0. Okay? And the reason for this being is that if we're going to look at each of these cases. Okay? And we're going to try to explain the reasoning behind them. So if f prime of x goes from negative to positive, what does the sign of f prime of x tell you about our function f of x? Well, if f prime of x is negative, it's a negative slope at that point. Okay? That means your function is going downwards. It's decreasing. Okay? So this test can also be used to find where the function is decreasing or increasing, where the f prime is positive. Positive. So if you look over here, this is a relative minimum. This is a minimum point. Why? Because f prime of x goes from negative, it's our decreasing interval, this is decreasing, f prime of x is going from negative, f is decreasing, to increasing. F prime goes to positive. So if it goes from negative to positive, that means you will have a minimum at that point. Okay? Let's look at some of these other points. Let's look at this one. Well, we know it's decreasing to the right of it. What about to the left of it? Well, the graph is clearly going up, so it's increasing over here. It's increasing until it hits that critical point. So it's increasing to decreasing. F prime is positive to negative. Positive, positive, negative. So this point will obviously be a max point, a relative maximum. Same thing over here, okay? This is also a maximum because the graph starts going downward over here. Now this one is where we get to use our third case, okay? Because you could see on our right that the graph is still decreasing. Our graph is still decreasing, still going down. It did not bend up. If it did bend up, it would be a minimum, okay? So this is neither. This is neither. It's a dud, okay? It doesn't give us anything because the derivative does not change signs at that point, okay? This is negative, this is negative. So this is neither a minimum nor a maximum. While these three are all maximums, or either a maxima or a minima, this one is neither. And you can see whenever it starts to like flatten out and then go the same direction, it will never be a minimum or a maximum because the derivative does not change signs at that point. Okay? And I said before, you could use this to find where it increases or decreases. Okay? So if you want to test where a function increases or decreases, so where it increases or decreases, well, you would find your critical points and what I would do, lay out like a number line like this. Your critical point A, critical point B, critical point C, and then test some arbitrary value on these little segments, okay? And if f prime is positive at a point on that interval, you would mark it with a plus. You would mark it with a plus. Use green. Green. So if it was if f prime was positive on a point between B and C, you would mark it with a plus. It's increasing on that interval. Okay, and it will always increase on that interval because A, B, and C are the only points where there's a critical point where it's either undefined or 0. Okay? And if the derivative was negative at that point between the interval, you would mark it with a minus sign. Okay, that's how I would traditionally do it. So if it was, negative at C plus 1, let's just say, so a little greater than C, then because there are no other critical points, it will be decreasing from C all the way to x equals infinity. Okay, as x approaches infinity, it will always keep on decreasing. Okay, and this thing is better to understand with actual problems, which we will do. Okay, it's a very popular topic on the AP exam.